Okay. Hi, good evening, ladies and gentlemen. Thank you very much for joining the panel discussion. Welcome to the panel discussion of advanced patterning materials and processes. Let's go on a treasure hunt. Today's topic is the treasure hunt. The subtitle of this session is What is the next exciting topics in NGL material and processes? Ask Captain in NGL. We have invited great captains as a panelist today. Okay. Today's tour guide is Masayuki Endo of Osaka University, and I'm Seiji Nagahara of Tokyo Electron. Thank you very much. Okay. So, purpose of today's adventure is to find the treasure in NGL material and processes. So where is the treasure items? So that can be in the UV, that can be in the E-beam, DSA, double patterning, multi-patterning, or nano-imprint, or any other next generation lithography. So we'd like to discuss about that. We need to know what's the real treasure. Where is the treasure? And until when we need to reach the treasure? Okay, so we need the leaders. Okay. So, as I said, we have invited the great leaders in next generation lithography, as you see, great leaders. So, first captain in this adventure is Professor Carlton Grant Wilson of University of Texas. Thank you very much for joining. And Jack Chenson of TSMC. Cheng-Il Olsen of Hynix, SK Hynix. And Dr. Ralph Danielson of AC Electronic Material. And Tomoki Nagai-san of JSR, young leader. Okay, and among them, so we would like to introduce Chief Captain. He is Professor Carlton Grant Wilson, University of Texas, as you see. Because he has already discovered great treasure. A lot of great treasure, like chemically amplified resist, or can be nano-imprint. I think he has sold the company already, I'm not sure. But he has found great treasure and awarded a lot of great award. So one is a Photopolymer Science and Technology Award in 2005 and many other. And 2013, as you know, he has got the Japan Prize. It's corresponds to the Nobel Prize awarded by our Emperor of Japan. It's a great pleasure, and we are very proud of having him in this industry, in this room. So, this is the image of today. He is the chief captain today, so please guide us. Okay, so today's route to the treasure is like this. After this introduction, so each captain will present short talk. And after each talk, we will have a short question and answer session. And then we will have a discussion session for each session. So we will discuss each of the topics. And also please ask a lot of questions to the panelists. Okay, so we would like to ask you to participate in this treasure hunt. Please imagine what is the next exciting topics in NGL material and processes. We will also ask you about your opinion in this room. That means we will point out you. Please be ready. but please don't worry if you don't want to answer or if you don't have an answer. Please point out other person next to you. Okay. So we also welcome very funny question, simple question, serious question, or any proposal, funny proposal. Okay. So from anyone in this room. Okay. Please enjoy the discussion with panelists. Okay, now let's join the treasure hunting and enjoy the rest of your life with the plenty of treasure. Let's go treasure hunt with captains. Now, energy material processing treasure hunt will start. Thank you very much.
We will start a short presentation from each captain. So the first one is Professor Grant Wilson. As Nagahara-san said, he's a very famous person. So he joined the department with University of Texas at Austin in 1993 after 17 years at IBM.
Yes, make it go away. I'm old. He's telling you I'm old.
I'll continue his bio. Please wait.
It's okay. I'm just telling you I'm old.
Okay? My nose, okay. So he starts.
So I'm not well prepared for this, I confess. I was even late to my own talk, so that's not a good sign. I spent my career at IBM and 17 years at IBM and now 21 years at the University of Texas working on that complex equation at the top, trying to support the reduction of the wavelength number and make the letter K become smaller. Over that period of time, we saw many changes take place, reducing the wavelength. It got down to 193 nanometers, and then we worked on new resistant materials for 193 nanometers. And then we tried 157, and had a lot of fun and a lot of work, but it failed. The 157 thing failed. So there will never be a wavelength shorter than 193, I think. The K factor when I started at IBM was running about 0.8 because the belief was that this was the size of the process window necessary to carry out the production of wafers with high yield and high efficiency. It's now down to 0.3. It cannot be smaller than 0.25. The index of refraction had always been 1, but Berlin made it 1.4 at 193. And we spent years trying to find a substance with index refraction higher than 1.4. We being the whole community, and we failed. So that's going to be it. 1.4 is as high as it'll get. And the sign of the capture angle of the lens is not going to get bigger than 1, I promise. And we're already at 0.9. So this is the end of it, and yet, we're printing smaller than 45 nanometer structures. So is this the end of Moore's Law? I don't know. We can't have it be the end of Moore's Law because we would all lose our jobs. There would be economic collapse. There would be nuclear holocaust and famine, and there would be plague would take over the world, and very bad things would happen. So we can't have that. We can't have the end of Moore's Law. So in the past, when it looked like Moore's Law was going to come to an end, for some reason, the community would pour money and brains on the problem until the problem went away, and it always went away. If you put enough money on it and enough brains on it, it eventually would go away. It always has gone away, and we've been able to continue up Moore's Law. So where we are now is we're trying to bridge the gap into some new structure, and the method is to pour more money. Can we bridge the gap? Well, Intel plowed $4.1 billion of after-tax money into attempts to bridge the gap. And this other company, what's the name of that company? $1.4 billion. That's enough money to send every student in Texas to college for free for many. And Samsung did a similar thing. And the proposal is that this is the method to bridge the gap. This is, EUV. You've seen it yourself many times before. And my picture of it is that if you follow the beam path, the light reflects off of that mirror, and 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 then to the And each time you say that mirror, you have to multiply 0.6 times 0.6, which is approximately equal to 0. And I contend that that is the probability of success of this technology. I've said that many times, and I continue to believe that it'll never make a wafer for profit. This is the light bulb. Actually, it's an older picture of a light bulb, but it's 100 times too dim and already somewhat complex. At any rate, what can we do? It's not good. There's no solution. So what we're doing instead is double exposure, and it's not easy. You can see even in PowerPoint, I had some difficulty with this. But surprisingly, people are doing it, and they're making product this way. It's an amazing tribute to the ingenuity of man and the care and cleverness of our people in this industry. But the problem is it's very expensive. And so what are the options? Well, before we look at the options, you should realize that there's a limit. This is the limit of resolution, of pattern fidelity. This is done by my colleague Don Eigler when I was at IBM. It's 1 atom dimension. That's as small as it gets. And the problem with this is that it's done by scanning tunneling microscopy on a substrate that's near the temperature of liquid helium. You pick up the atom with a tip and move it to the position that you want, and lift up and let it go. And unfortunately, it's done pixel by pixel, and it takes about 1 minute for each pixel. So the throughput of the process is very, very low. Here is the scanning tunneling microscope manipulation, and on this axis, so it has very high resolution. Small structures can be built, but the throughput in micrometers per squared per hour is incredibly low. So it's there. And Don Tennant, used to be at Bell Labs, now at Cornell, published this interesting chart that shows the resolution has an interesting log-log relationship with aerial throughput, with the exception of one technology, which is here. And that captured our attention. At the University of Texas, of course, we've worked hard for, I guess it's 12 or 13 years now, and developed this step-in flash imprint lithography process in which one builds this template that I think most of you are familiar with, which is expensive and slow to make and difficult and challenging. But once you make it, you can replicate it by just capturing photopolymerizable liquid in the gap between the template and the substrate, shining light through the back with no lasers, no lenses, pretty straightforward, and then just step and repeat the process. And the remarkable thing about it is that no matter, to my amazement, it works better than it should. I'll just say a couple things quickly. One is you can print more than one layer at a time. The other is that you can print dots and lines that are perpendicular to one another, all at the same time with perfect resolution and replication. And there are a lot of things it'll do that it shouldn't do. This is one of them. It's filling 14 nanometer posts, which means that there are cavities in the template. And if you ever have taken a water glass or something and turn it upside down and stick it into your dishwash, into your sink, it does not fill up. So there's no reason why all these little cavities should be filled up, but they are, every single one. trillions per square inch of them filled up. And that's just luck, and it has to do with the special capillary forces that occur in such small structures. But it's a wonderful technology. And here's someone who came to look at it, and he's looking at the first fully patterned 450 millimeter wafer, and it was done by imprint lithography. So our inspiration with it at the moment has not been, believe it or not, semiconductors, but hard disk drives. And the hard disk drive people need to pattern their substrates, at least that's one option for advancing their technology. And the only way you can write structures which are on the neighborhood of 10 nanometers in dimension of the sort that are required to push this technology is by electron beam lithography. And of course, it's too slow. So the idea is to write templates with e-beam lithography and then pattern the systems by imprint. And the problem with this, I thought, well, gee, we're going to sell a lot of imprint tools and my children will get new shoes. But the problem was that the way they write them was with this rotating master system, and it's just too slow. It takes a month to write one template. It costs over $1 million, and there's never been a full template written, to the best of my understanding. So we need some miracle in order to make these templates and to enable imprint lithography for this purpose. And that inspired us to engage in the block copolymer miracles of copolymer characteristics. We weren't trying to make semiconductor structures. Honestly, it was this imprint application that inspired my lab to work on the things. And it is a miracle that they will correct electron beam patterns and make them beautiful. And even if you only write every fourth one, it will fill in the missing blanks, which means instead of taking a month, it only takes a week to write the template. And all of this has been fully demonstrated. And in fact, the machines that will print these wafers at about almost 300 wafers an hour on both sides have been demonstrated and exist. And everything is ready to go. The production pathway has been demonstrated by HGST. Meets the target fab tolerances. This is actually the patterned media at 1 teradot per square inch. But unfortunately, not small enough. And therefore, that inspired our work on the block copolymers. So I think the combination of block copolymers and patterning tricks like sidewall double patterning and so forth that are expensive and difficult to carry out should be used, maybe even EV, should be used to make imprint templates and use that parallel transfer technique to print the product. That's my personal theory of the future of the operation. I confess that I'm prejudiced.
Thank you very much. So, if you have any questions from the audience? So,
just one remark. The difference of the needle is actually purple needle instead of pink.
So this is one of the very interesting questions that you have to ask yourself, and I think you should think about, is why is all that money going to EV? When in fact the total amount of money that have been spent on developing to the time that molecular kits was sold, the total amount of money that was spent in developing it was about equal to the cost of one EV machine. The entire technology was developed with about that much money, and the industry has not supported this almost at all, with the exception of Toshiba, to whom I give great thanks.